About basic electric measuring instrument, and for that case we will discuss about Wheatstone bridge, Maxwell bridge, different types of AC bridges and sharing bridges. So first, what is Wheatstone bridge? Wheatstone bridge is a basic setup with resistance. Using this bridge we can calculate unknown resistance that used in a circuit. So if we draw the diagram, that is the basic diagram of Wheatstone bridge. Using this Wheatstone bridge we can calculate unknown resistance that used in a circuit. So how can I measure, or what is the principle of this diagram? So we make a circuit like that. So we have to, there is a key attached with the galvanometer, and shifting this key, there is a key. Shifting this key, we can find out the null point. What is the null point? Null point is such a point that where the current through the galvanometer should be equal to 0. So to establish this condition, we divide the current through the circuit. Let us assume total current is I1 that flows through that path, and this path, at that point the current will divide into two paths. So let us think the current through R1 should be equal to I2, and the current should be R3 equal to I1 minus I2. And next thing, if we assume the galvanometer current is Ig, then we can easily see that at that point current will be divided again two parts. So if this path has current Ig, then this path current will be I2 minus Ig. Again, if we consider that path, let us consider that point A, B, C, D. If we consider point D, then at that point the current will be like that. So the current will go through this, that will be I1 minus I2, I1 minus I2. It will divide into two parts, so it will be plus Ig. That path, the current will be I1 minus I2 plus Ig. So let us consider, if we find out the null point, then we know that the current inside the galvanometer will be equal to 0. At that condition, what will be our outcome? If we consider that loop 1, and that loop 2, then our outcome is I2 into R1 minus I1 minus I2 into R3 should be equal to 0. And another way, I2 into R2 minus I1 minus I2 into R4 will be equal to 0. If we consider I is equal to 0, that means we've already find out the null point. So this will be the two equation we can get from the Kirchhoff voltage law from the loop 1 and loop 2. Subsequently we can get the condition that can satisfy the nullify condition or nullity condition. What will be the condition? The condition will be R1 by R2. As we see that two equations are similar. So if these two equations are valid, then we can say that it possible when R1 by R2 equal to R3 by R4. R3 by R4. R1 by R2 should be equal to R3 by R4. That means we can say R1, R4 equal to 2 R3. That is the condition where we get the null condition where the galvanometer current is equal to 0 using the key, or this key is called jockey. So that is the condition of nullity. Using this Wheatstone bridge, we can calculate unknown resistance. Let us consider R1 is known resistance and R2 is also known resistance. Let us consider R4 is unknown. So we can choose R3 such a way that we can get null condition. And from this equation we can calculate R4. What will be the R4? R4 will be R3 into R2 by R1. That means, as we already decided, R2 by R1 should be equal to constant. So it depends only on the R3. If we change R3, then according to this formula, we can get different R4. So using this formula, we can calculate different resistance used in the circuit. One thing, as here, this also applicable for DC as well as AC. As we know that resistance only gives the resistive effect. It can't create any inductance or it can create any capacitance within the circuit. It cannot store any amount of energy. So, or it cannot create some phase difference. So, in both cases, AC and DC, we can apply this rule to check the null point or to find out the unknown resistance where the circuit should be purely resistive. Then we can use it AC as well as DC. But now we will see, if we do not find out the null point, then what will be the expression of the current IG. So we will definitely find out the equation for null current. What will be the equation? So first equation will be I2. So let us consider this is loop 1, this is loop 2, and this to this means that to that cases, the whole circuit we can consider as a loop. So as here three different parameters, current parameters are there, I1, I2, I3. So IG. So we need three equations. That's why we choose three loops. So from first loop we can get R1 minus I1 minus I2 into R3 plus IG into RG. Next, that will be I2 minus IG into R2. That will be minus I1 minus I2 plus IG into R4 minus IGRG. That will be equal to 0. And last one will be, we consider whole circuit, then it will be I2 R1 plus I2 minus IG into R2 plus RB I1, it will be equal to VB. Let us consider VB is the potential difference along the circuit. This will be three equations. So from that equation we can get IG. What will be the IG? IG will be equal to, let us rearrange this equation in such a way that I1, what will be the coefficient of I1? Minus I1 into R3. Then what will be the coefficient of I2? Coefficient of I2 will be plus I2 into R1 plus R3 plus Ig Rg equal to 0. Second one will be minus I1 R2 R4, then plus I2 R2 plus R4 Ig into Rg minus Ig into Rg plus R2, that will be 0. And the last one, which I1 RB plus I2 into R1 plus R2 minus IgRB IgR2 equal to VB. So from 3 equation 1, 2 and 3 we can find out the root Ig, that will be equal to determinant of minus R3 R1 plus 0 so that will be, if we reduce that column, then it will be RB R1 plus R2 and that will be VB divided by minus R3 R1 plus R3 Rg R4 minus R4 R2 plus R4 minus Rg plus R2 RB R1 plus R2 minus R2. That will be the equation of Ig. Now we can see that if we see on the denominator and numerator also, then what will be the result? If we see the upper part of this fraction, that will be minus R3 R1 plus R3 0 R4 R2 plus R4 0 RB R1 plus R2 VB should be equal to 0. So if we calculate this upper term, what will be the value of the determinant? The determinant will be VB into minus R3 R2 plus R4 plus R4 into R1 plus R3 VB into minus R3 R2 minus R3 R4 plus R1 R4 plus R3 R4. R3 R4 will cancel out and the remaining term will be VB into minus R3 R2 minus plus R1 R4. Now if we consider that the null condition I1 null condition was R1 by R2 equal to R3 by R4. So from here we can see that R1 R4 equal to R2 R3. So that will be 0. For the null condition we can see that this condition, and at that condition Ig should be equal to 0. That means it does not depends on the lower part of this fraction. So if we get the null condition, that means the value of Ig does not depends on the lower part, or this is the determinant. So that means if we interchange something in this determinant, that has no effect on Ig, as we know that at the null point Ig should be equal to 0. So if we interchange something, or if we change some resistance in that part, so it will be incorrect. So from here we can tell that if we interchange the galvanometer resistance with that the external resistance RB, then also at the null point, then also we can get the condition to achieve the nullity. So this is the discussion about the Wheatstone bridge. So now, using this bridge we can calculate unknown resistance, and we also see that if we interchange the external resistance and the galvanometer resistance, there is no effect of the nullity condition. And another thing, sensitivity of the Wheatstone bridge. So if we study this determinant, we can see that if we change the position of RB and RG, so we can see that the sensitivity of the Wheatstone bridge will be high when R1 should be greater R2, and also R3 will be R1 should be greater than R3 and R2 should be greater than R4. At that condition, we can get the better sensitivity of the Wheatstone bridge. That means if we reverse this condition also, that also be valid. That means if R3 is greater than R1 and R4 also greater than R2, at these two conditions, we can get better sensitivity of this Wheatstone bridge. So either that means the resistance inside the galvanometer should be attached, one end should be attached with the higher resistance junction and another end will be attached with the low resistance junction point. That is the sensitivity of the Wheatstone bridge. And another thing, if anyway we can create a condition such that R1 equal to R2 equal to R3 equal to R4, if we create the condition R1 equal to R2 equal to R3 equal to R4, that also satisfy the nullity condition. So if we create that condition, at that point we can get the base stability of the Wheatstone bridge. So for the better stability, we have to remember that condition, and the base stability, the condition will be R1 equal to R2 equal to R3 equal to R4. So that is the thing about Wheatstone AC bridge. So the structure of AC bridge is like that. Here we take some instrument, whatever it will be. It can be resistance, or it can be inductance, or it can be capacitor, either resistor or inductor or capacitor. If we take purely resistor, so it is converted as a Wheatstone bridge. So not required to means it simply convert into Wheatstone bridge, not required to study further for the purely resisting case in the AC signal. But if we introduce inductor or capacitor, then what will be the effect in the AC or alternating current? So first thing, within AC, this inductor or capacitor gives two effects. One is resistivity. Resistivity means it can resist current to flow through the circuit. So it will both can give resistivity, means both resist the current to flow the circuit. And another thing is phase. It can change phase between voltage and current inside the electric circuit. So these two phenomena happens within AC if we use inductor and capacitor, or both within a AC circuit. So for that case, what will be the null condition or nullity condition of this diagram? So here also we apply the KVL and KCL rule, and we already know that from the previous figure based on this, we already decide what will be the condition of the null condition. So now let us consider these two effects, this resistivity and create some cases between voltage and current. These two effects called as impedance of a circuit, or impedance of a element, or element C, that kind of thing. And we already know that for inductor, what will be the impedance? If we consider that inductor has some resistive effect, so L can be considered. The impedance of L can be considered at ZL. If we consider that it has some resistive effect, so it will be R plus J omega L. R plus J omega L. That means R gives a resistive effect, and so if we take mod of JL, it will be equal to R square plus omega square L square. And if we take the capacitor, so what will be the impedance of the capacitor? If we let us consider the resistivity of the capacitor, it also be R. So ZC will be equal to R minus J by omega C. It is also a complex quantity. As we know that this complex part, it can't contribute resistivity. Why it can't contribute resistivity? We will see after some time. So what will be the mod ZC? Mod ZC will be equal to R square plus 1 by omega square C square. So that will be the impedance of capacitor, resistive capacitor and resistive inductor. So for that case, our unknown parameters are means two unknown parameters are there. One is resistivity and another is phase. So now we will discuss about what is phase. So if we consider simply case for inductive circuit, purely inductive circuit. If we consider the purely inductive circuit, that means the impedance of the inductor is omega L. So if we what will be the equation of the circuit? So if the voltage is V supplied on the circuit, that if you consider it is V equal to V0 sin omega t, and we can show that L di dt will be equal to L di dt plus V will be equal to 0. V equal to minus d phi dt and phi equal to Li, so it will be minus Li dt. So we can write that L di dt plus V equal to 0. And if we consider I equal to I0 into sin omega t, then if we put I value in the equation, what will be the result? L omega cos omega t plus V equal to 0. So V will be equal to minus omega L cos omega t. That means if we multiply minus, it will be omega L cos of omega t and omega L cos of sin of 90 minus omega t. And if we take minus from that, then we can get omega L sin of omega t minus pi by 2. That means here we can see that current is leaded pi by 2 with respect to voltage. Here current leads pi by 2 with respect to voltage. So we can see that it can create some phases within the circuit. That's why the impedance Z, we can represent it as a mod of Z into, as we know that it is a complex quantity, and in general rule to represent a complex number, we can represent it as a Z equal to Z into the power I theta. So for every case, let us consider that is Z1, that is Z2, that is Z3 and that is Z4. So for each and every case, we have to balance the resistance. To maintain the nullity, we have to balance the resistivity as well as the phase within the circuit. So for that case, from the directly we can get from the Wheatstone bridge circuit, we can get Z1 into Z4 equal to Z2 into Z3. So here we see that Z1 equal to mod Z into mod Z4 into e to the power I. Theta 1 plus theta 4 equal to Z2 mod Z2 mod Z4 mod Z3 into the power I. Theta 2 plus theta 3. So to maintain this two condition, as we know that there are two unknown parameters are there, we have to if we make the nullity, if we want to get the null condition of this AC circuit, so we have to make two conditions. One is, we already know that if we balance one complex equation, so here we can easily see that mod Z1 mod Z4 that should be equal to mod Z2 mod Z3. It will be one condition that gives the purely resistivity of the circuit, and that is simply connected to the question bridge. And another condition will be theta 1 plus theta 4 will be equal to theta 2 plus theta 3. That gives the first condition, and this gives the second condition. Next, we have to study. This is the basic principle of AC bridge. Using AC bridge, we can identify unknown impedance that used in the circuit. We can calculate or we can identify what type of impedance used in the circuit, and as well as we can calculate what is the impedance of this component. We can easily calculate from the null condition of the circuit. That is the null condition of the circuit. That two conditions are there. So now we are going for Maxwell bridge. We are going to Maxwell bridge. So what will be the condition? The condition will be Z1 equal to, we know that it is R1, and Z2 is equal to R2, and Z3 is equal to Rx plus J omega Lx, and Z4 it will be Rs plus J omega Ls. So if we multiply R1 and R4 according to the null condition, so Z1 into Z2 is equal to, so Z1 into Z4 equal to Z2 Z3. So if we calculate this, Z1 is R1 and Z4 equal to Rs plus J omega L, that is equal to Z2. Z2 means R2, and Z3 equal to Rx plus J omega Lx. That is Rx. So if we balance this equation, R1 Rs plus R1 J omega Ls equal to R2 Rx plus J R2 omega Lx. So to balance the condition, we can simply equate the real part of LHS and real part of RHS. That will be equal to R1 Rs equal to R2 Rx, and simply we balance the imaginary part of this complex equation. That will be equal to R1 omega Ls equal to R2 omega Lx. So as same omega is used in the circuit, so omega is invariant, so we can remove it out. So from here we can calculate Rx will be equal to Rs into R1 by R2. So using varying this Rs, we can calculate the unknown impedance of the inductor. So what will be the Lx? Lx will be equal to R1 by R2 into Lx. Now, how can we do the experiment? For getting the null condition of this AC circuit, we can use a headphone. For this point A and point B. We can use a headphone. We can attach the bipolar headphone on this, and we can get, at first we adjust minimum tone of this circuit using balancing Rs. We have to adjust Rs such that we can get a single tone that is good enough for hearing, that is good enough. So we suggest Rs first. Then we have to reduce this signal up to 0. We have to totally reduce the signal, balancing Rx within the unknown impedance. So at first we have to make a certain RS such that the tone in the headphone is hearable or comfortable to hear. After that, we have to reduce it and make it 0 to get the null condition using RX. So here to maintain these two conditions, we have to that's why we use two different resistance to maintain the null condition of this AC circuit. For the Maxwell bridge, we simply use a capacitor here. Instead of using this inductance, we have to use a capacitor in place of R1. R1 there will be one resistance, as well as we have to use one capacitor parallelly in the circuit. So for that case, for particular that bridge, what will be the nullity condition? The condition will be same, but we have to calculate it. Then let us take what will be the R1. We have to find out that only. Z1 equal to R1. Z1 is impedance, so 1 by Z1 equal to, as R and capacitor C1 is in parallel, so we can calculate 1 by R1 plus impedance of the capacitance is minus 1 by J omega C, J by omega C, so that will be J by omega C, so that will be 1 by minus J omega C, so it will be I to the power 4 means I square, that will be minus J by omega C, that is I square, that means plus J omega C. So if we calculate it, R1 1 plus J R1 omega C, so Z1 will be equal to R1 plus 1 plus J by J into R1 omega C. If I put here Z1 equal to R1 plus J R1 omega C, then what will be Z2? Z2 will be R2, and Z3 will be Z1, Z3 will be Lx plus Rx plus J omega Lx, and Z4 will be simply Rx. So if we calculate this unknown inductance, so we have to maintain the nullity condition. So if we put in this condition, if we put this impedance within the equation, that will be R1 by 1 plus R1 omega C into Z4 means Rs is equal to Z2 means R2 Rx plus J omega Lx. So it will be R1 Rs equal to 1 plus J R1 omega C into R2 Rx plus J R2 omega Lx. So that will be R2 Rx plus J omega Lx R2 plus J R1 omega C R2 Rx, and next one will be minus R1 R2 omega square Lx C. So here also we can equate the real part from LHS and RHS, so we can get R1 Rs equal to R2 Rx minus R1 R2 omega square CLX. So from this condition we can get Rx. The Rx will be R1 Rs plus R1 R2 omega square C into Lx divided by R2, and as well as we can get omega Lx R2 equal to R1 minus R1 omega C R2 Rx. So it is independent of omega. So from here we can get Lx Rx will be equal to R1 R2 Rx R1 R2 C Rx by divided by 2. So R1 R2 C. So from that we can get unknown impedance of the third terminal. So here also we can use the help to check the null condition on this. So this is the things about Maxwell. So we can finish.